minimum wage, you know, and like try to pay some.
We might do it with two.
Okay, let's get started. Hi everybody, how's it going?
Hi.
How's everybody feeling?
All right.
Good? Ready to hear about my health? Yeah.
Well, how you doing?
All right, cool. You asked. You agreed. So I went to the doctor. I couldn't see the doctor on Monday. I saw the doctor yesterday. And so the symptoms are like low fever and myalgia, right? All my muscles are killing me. I don't know. So he's like, huh. So what do you think? What do you think my doctor thinks it is?
Brain cancer.
No, come on. What would you do if you were a doctor?
He thinks you test. Iron depletion.
Oh, those are all good.
Cold.
You know, he was like, I think it's probably a virus.
And you're
Probably
like,
a virus.
no
You know,
shit.
so, you know, rest. And I was like, Doc, like, I'm terrified. I've never felt like this before. You gotta do something better than that. Give me a Paragen test. So he agreed to give me a Paragen. I was like, I want you to test me for Lyme disease. I want you to, because I feel crazy. The fact is, so I got all those tests. They took so much blood. They took like a pint of blood out of each arm. So I'm still pretty weak, but like knowing that I'm getting tested, maybe it's psychological, but I like feel a little better. My hands are still a little weak, so bear with me with my right. But I think, you know, I don't think I'm going anywhere. It's okay, you know, you're praying people, it's okay for you to continue praying. So that's just let's get back. But it's probably, you know what else he said, which is interesting, is like, you know, it might just be the flu, and like the weakest flu you ever got. You're getting all like the flu body pain, but not the like other stuff, which would be interesting, I'm sure, right? So anyway, stuff to look forward to as you get older. Mystery diseases. Okay, so today, obviously, I have an adult brain, so I'm probably trying to do too much. But if we can be ambitious, what I'd like to do is just spend just a minute recapping what we studied in the last lecture. Because, you know, we studied a really simple protocol that I feel like we kind of all came out the gate kind of knowing intuitively, even if we hadn't studied it in the context of the networking, right? Tell me that you got the message, and then I know you got the message, I'll stop sending it, right? But we'll spend a minute talking about that. And then there's just sort of like little sidebar that I want to get into. You know, I discussed before in the context of the network models, how like, wow, we know that reality doesn't exactly match the async or the sync model, right? But they're nevertheless useful for framing our discussions. And this conversation becomes even more nuanced in the context of fault models. Because it's tempting to ask, if you're a programmer who's used things like TCP and connected to computers on the other side of the internet, like, what does the omission model mean? Like, what are omissions? Like, do I lose messages in real life? So I want to kind of map things you may know from real life to this model and kind of argue that this model doesn't exactly match real life. It's sort of strictly uglier than real life, which is exactly where we want to be. And then we can use this model to model the sorts of bad things that can happen in real life. I want to spend some time on real life. And then I want to get to the real matter of today, which is going beyond reliable delivery and introducing a new, substantially harder to reason about and understand protocol called reliable broadcast. I'm going to define it formally, but it's the idea of ensuring that, in some sort of atomic sense, everyone in the group either gets a message or nobody gets the message. Right? So atomicity of dissemination of a message to a group. Needless to say, this is going to turn out to be more complicated than just making sure that one person gets it. Okay? And then, if we have time, I want to kind of have this, I'm going to bridge this conversation from reliable delivery protocols over into replication and have this kind of, this cosmic thing around, you know, what is fault tolerance really? And what is replication really? And we'll do that if we have time. If not, we'll do that on Friday. Okay? So, you know, fault models. What fault model did I say we were going to mostly live in this class?
Omission plus some.
What was wrong with that? Yeah, why didn't we like the omission?
It's not tolerant to everything else.
Sorry, go ahead.
It's not tolerant to anything else outside of it. Like,
Yeah, but I mean,
seem
like, what are the things outside of it that we think might happen? Like, I don't care if it's not tolerant to things that I don't think are ever going to happen in practice. What are some of the things that might happen?
You mentioned that corruption, like, or I think what
Yeah,
might have been packet
that's kind of
loss.
like the. It's not the only example. It's like, remember, we drew this picture. It's concentric squares, and then somewhere out here was the omission model. And we said, well, there's one model that's bigger. There's only one model that's bigger, because in the Byzantine model, literally anything that can happen can happen. There's nothing that contains the Byzantine model. All bets are off out here. And I argue that, like, there's this one super common thing that doesn't cleanly map to the omission model, and that's corruption of data on memory or in transit, or both. And I argue that with simple, well-understood, computationally efficient techniques, we can identify those corruptions and turn them into omissions. Right? So in that sense, we can cut, with that patch, a lot of researchers will argue that the omission model is arguably the right place to be when we're designing protocols and putting things are possible. Other researchers won't argue that. It depends on what your threat model is. You know? It's very often the case that software that was designed to operate within a single data center can make more optimistic assumptions about how, what the behavior of bad actors might be, right? Because you actually maybe have physical control over the physical wires, and physical racks, and so on and so forth. That's not to say that somebody could come into your data center and do some havoc. We think that's a vanishingly small probability. So the world lives here. I feel like maybe this is a good time to tell this anecdote. I was at this conference, actually, it was Baby's first academic conference, SOSP 2009, and Yahoo Research gave a presentation about Byzantine fault tolerance. And the presentation was basically this. They looked at the last 5 or 6 years of production scale outages at Yahoo, which at that time was a company that you had heard of and people thought was important. I realize it's not true anymore. Now imagine that it was like Google or something like that. Right? So they looked at 5 or 6 years of production outages, and they asked this question, analyzing the data, doing the postmortem, how many of those production outages would have been prevented if their software, in particular coordination software like Zookeeper, which we'll talk about later in the class, had been Byzantine fault tolerant rather than just omission fault tolerant? And the answer was, how many do you think?
All.
None of them. So it turned out that with error correction codes in place, there was never a single incident that affected Yahoo's bottom line that would have been prevented by BFT, by Byzantine fault tolerant software. And that's how they justified continuing to not invest in the research. Right? So it's, data's a full anecdote, your mileage may vary, but that's why Yahoo said their research group was developing omission fault tolerant rather than Byzantine fault tolerant. Questions? Yeah?
What kind of things cause an outage like that are not fault tolerant in the Byzantine model?
Oh, well, let's see. So, are you asking what in general can cause a production outage that doesn't involve like a hacker or a haywire machine? So, there's a really great paper that I'll post on Piazza from OSDI 2015 or 2016 called "Simple Testing Can Prevent Most Critical Failures." Right? It's a great title. And it basically looks at production outages across all enterprises that have had press about it. So it's not like an internal thing, it's like from the outside. And they break down the causes, and you shouldn't be surprised to learn that like configuration errors, or maybe the lion's share, it's like 60%. The code's fine, the code's doing exactly what it's supposed to do. Ops pushed out some config change that made it to some of the servers, but not all the servers. And now the servers are disagreeing about what protocol they're supposed to be talking to each other. And things like that are like super common. And then just simple bugs where, there's some race condition that gets you into a branch you didn't think of in an infinite loop that will never terminate because the termination condition was read from some file that somebody wrote wrong or something like that. So it's infinite loop bugs and things like that. Yeah?
Just wondering, so the example of, some machines had a new configuration, some didn't, and so they weren't agreeing on the protocol, but isn't that kind of the Byzantine fault tolerant model, that some machines could be doing whatever they want to do?
That's a great point, that's a brilliant point. Yes, however, it all depends where you define the boundaries of your system. Like, let's say that protocol was Byzantine fault tolerant. Does that mean that it's so Byzantine fault tolerant that it'll work even if you give it the wrong config file, even if you give it a config file filled with boogers instead of JSON? So you're right, except that when you say what's Byzantine, you say what's outside the system and what's inside the system. And you say this is an input to the system, and at some point you're not going to be like, I am correct for all possible inputs, right? Even the corrupt ones, right? So you're right, that's a fair point, but I don't think that if they had written the Byzantine fault-tolerant consensus, it would have helped them if somebody pushed the janky config, because they would have assumed, well, assuming your config is correct. Yeah?
So it's like saying my program is so fault-tolerant that it does the right thing even on a computer that doesn't have the program on it.
Right, exactly. So you have some trusted base, like I am running the program that I say I'm running, my computer actually computes. I'm on a computer where 2 + 2 actually equals 4. All these things. All right. So good. So that's a recap on fault models. Is there anything to say about reliable delivery? Let me just turn over to the class, and I'm going to make quick work of this. Do you have any questions? questions about reliable delivery? Was anything missing there? All right, so let's talk about the real world. The first thing I want to say, and this is something hopefully is going to come up a bunch more times in this class, some of the stuff we're going to study in this class are building blocks that can be used to build more complicated things. And sometimes the stuff we study in this class are protocols that are more or less orthogonal from each other. And if protocols are orthogonal from each other, they can sometimes be stacked in interesting ways, right? And so we studied reliable delivery. But in practice, people very often would like to have reliable delivery and first in, first out delivery with some kind of economy mechanism between them. But because they're completely orthogonal, we can imagine a stack in which we just say, look, there's a FIFO ordering module that is built on top of reliable delivery. And sometimes it's useful to think about the stack as something that's essentially passing through method calls. So you imagine, like, down here we have, like, the network, which, as we said, is an asynchronous network, makes no guarantee about the order in which messages are delivered, makes no guarantee about messages being delivered. And you can imagine the idea of, like, a primitive send operation into that network, where you send into that network, and hopefully it comes out the other side, but not necessarily. And then you can imagine transiting this whole stack, where you have, like, an application level send, which calls FIFO send. FIFO send calls reliable deliveries send. And then reliable delivery calls bare bones send. And when a message comes in off the network, it traverses reliable delivery module, which possibly sends ACKs. And then it traverses the FIFO module, which decides when it can be delivered. And then ultimately up here we have delivery. Down here we have receipt of a message. Does that picture make sense? Right? So you imagine what would that look like in lamp orchard? So we have Alice and Bob, and they're doing reliable delivery and FIFO delivery. What would that look like? It would look like, here's my Alice's, application level send. I send a message. Oh, by the way, it's FIFO delivery, so it doesn't just have the message payload, it also has the number, right? And then we have, so it's AS, and then we have RS, and then we have S, all happening on Alice's side. And then over on Bob's side, when he gets the message, he receives the message, and then he sends the acknowledgement, reliable deliver, and then ultimately he delivers the message to his application. That's it. Those two protocols have now been cleanly stitched together. Why do I say cleanly? Well, because they're completely orthogonal. They have nothing to do with each other. We can just sort of pass information through one and out through the other. And we can imagine, building tall stacks in this fashion. Right? We might imagine saying, well, I'll leave it here for now. So it's going to be the case that we're going to talk sometimes in class about completely separate things. We're going to talk about building things out of other things. And then sometimes we're going to just talk about stacking things. Does the picture make sense? The idea that this is an API, this is an API, this is an API. You could have just called a reliable delivery API. Heck, you could have just sent the message and prayed. Right? There's a bunch of different places in the stack where you can interface with it and pick out the results. Yeah? Some of you look a little confused. Is it a weird picture? Stacks are a thing. Okay. Models versus reality. What can we say about this? So we live in the omission model, which would appear to say, if I send a message, there are sort of two possible worlds. There's the world in which that message never makes it to its destination, and there's all the worlds in which that message makes it to its destination, possibly at different times. But from the point of view of fault tolerance, there's really the two possibilities, right? Now, if you've programmed communicating systems, you've probably done so by identifying the address of a server that you want to connect to, and then opening up a TCP socket to that server by calling connect. And then connect returns a file handle, and then you do I/O on that file handle by reading and writing, with this illusion that you've got this sort of endless stream of bytes between you and that endpoint. And then at some point the session closes. Right? And in TCP, when you have that persistent connection between these two endpoints, what kinds of guarantees do you enjoy on that channel? First of all, is the channel unidirectional or bidirectional? It's bidirectional, right? I can write to it, you can write to it. So you sort of have, in some sense, two, theoretically infinite byte streams. And what guarantees do we enjoy on those things? FIFO and reliable delivery. So you sort of get this stack, right? But with the caveat that that's within a session, right? So a session, you have a timeline, right? A session begins from the point of view of the client with a connect call. Then you have writes and reads. And then at some point it ends with a close, right? And it's only between the connect and the close that you have these stream semantics. You have there's this impedance mismatch between this model in which essentially all we're doing is sending what you might call RPCs, right? Individual messages that have a beginning and an end and then they're done. And this communication substrate that is session-oriented, that has like richer semantics and that. This is actually really frustrating because a lot of distributed protocols are described in terms of primitive atomic messages, RPC, remote procedure calls, right? Do this work. And the cleanest way to implement RPCs over a mechanism like TCP would be when somebody sends a message to somebody else, you open a connection, you send the bytes, and then you close the connection. But of course, in practice, we don't do this. Why would that?
Because you don't get the guarantees of order FIFO and reliability. FIFO within.
Well, that's true. That's true. Although I would argue that if you're in an RPC model, you don't necessarily care about the guarantees. And sometimes TCP is overkill. I think the main reason why people don't do it is the overhead. That like it costs an awful lot to do a three-way handshake, and then close stuff up every time you want to send a message. So what you do in practice is you try to minimize how often you do connects, and you try to pack as many RPCs in here as you can, and then you get the added benefit. Yeah, the RPCs that you send within the session happen to be first in, first out. But the fact that sessions don't last forever, sessions get closed when there's a hiccup on the network. So now you have to write all this code that periodically detects that the connection's been closed and reconnects. And it's not exactly clear what the guarantees that are session-oriented mean in a reality in which you, over time, have a great many sessions whose boundaries are not very clearly defined. What session am I in, and so on. Yeah?
What does RPC stand for again?
Remote procedure call. Yeah, sorry about that.
But you wouldn't want the RPC calls to be in the order that someone expects them to be in, right?
If there's that expectation. But the other thing is, like, if we had a great protocol for doing RPCs that wasn't TCP, you might just implement FIFO delivery as a separate part of the stack, rather than assuming it was being given to you by FIFO. Because in some sense, what I want is FIFO delivery over the lifetime of my application for all of its RPCs, not FIFO delivery during the lifetime of my session, which may or may not be coupled in a meaningful way with the lifetime of my application. I'm saying all this to say the mapping between the model and the reality is by no means clean, but the model is a good model because anything that can happen bad in the actual world is going to be modelable in the omission model, but not necessarily the other way around, right? So in reality, because TCP sessions can be closed, you can get uncertainty around whether a particular, so you're in this TCP session, and you send a bunch of RPCs, and then you send RPC number 27, and then you get some kind of socket timeout. Did the other guy get RPC 27 or not? You don't know. So probably what you're going to do is you're going to open a new TCP connection and you're going to send it again. And so sometimes you run into all these issues, even though you're using TCP, like redundant delivery, and is it idempotent? And am I going to have to write some idempotence layer in my application, even though TCP is trying to ensure idempotence? TCP can only ensure idempotence within a session, and my application requires idempotence throughout its entire lifetime, right? So bottom line, what are the various problems that we say that can happen in TCP, and they typically happen at session boundaries, where your application looks like there was this TCP session, and there was this other TCP session, and there was this other TCP session, and the shit that happened out here, you don't know if it belonged out here. You know, like the stuff at the boundaries is jacked up. And this is where we can explain the weird stuff that happens here using arguments around message omission. So another real world thing we're going to talk about a lot in this class, and it's become really relevant really soon, is this concept of a network partition. Partition. Who's heard this term? Okay, anybody want to give me a provisional definition of a network partition? What's a network partition? You raised your hand, right?
I did. You asked if I heard the term.
Yeah, well, that gives me a warning to you. There's no wrong answers, I'm just curious.
Okay. I guess just taking part of the overall network and then doing some sort of operation on part of it, or considering part of it as a separate chunk.
Yeah, so that's the right way to think about it, except we're going to think about network partitions as a non-deterministic event out of our control, a particular type of failure that does that. Not because we wanted to do it, but because it just, you know, sometimes we do things and sometimes things just happen to us, right? So you imagine a network of communicating computers. You know, when people first started writing about this, you imagine the most trivial network partition would be some kind of event that allows these computers to keep talking to each other and these computers to keep talking to each other, but for them not to be able to communicate across this bar, right? Obviously, this can cause pretty serious situations if we have protocols that, for example, require you to hear from everybody before you make any progress, right? So, for example, we looked at three implementations of causal delivery. One of them used vector clocks, and in the event of a network partition, the people on both sides of the partition could keep delivering things causally. And then when the partition healed, maybe things could get cleaned up. But the one where people waited for an act from everybody before they sent their next message would hang up. Yeah?
You got subnet feed partition?
A subnet?
Yeah.
No. I mean, a subnet is just a logical subdivision of a logical space, right? So the idea is, but now what event am I talking about? Well, in practice, right, in a data center, machines are arranged into racks, and the machines on the rack communicate with each other, over their top rack switches. So if this machine wants to communicate with this machine, let's say, it's a very short hop to communicate. But if a machine in this rack wants to communicate with a machine in this rack, there's like I forget what it's called. It's not an L2, that's caches. There's some like higher level switch that they need to transmit through. And then of course, if you want to, and then these racks are like arranged into rows, and if you want to talk to another row, there's like a really big switch you need to go through. Well, needless to say, these switches are hardware, they're made by people, and these switches fail too. These switches crash just like computers crash. And what would happen if this were to crash and these nodes were on these two things? We would get exactly this, right? I can talk to all the nodes on my rack, but I can't talk to the nodes on this other rack because the switch we would have needed to traverse to do so is not there. Now, more modern networks, close to fat tree networks, try very hard to have redundant routes between all pairs of things to make this vanishingly unlikely, but like, something can go wrong at all, right? Okay, so that's and then of course, on the wide area network, you can imagine there's a lot of different reasons why this might happen, right? Because there might be some BGP router you have to go through to get from one place to another, and that router's crashing or something like that. What's more interesting though is that this is just a particular obvious form of network partition. Some of the more insidious ones might look like, here's an insidious one. There's a client who can see both sides of the network, but they can't see each other. So that, you can see how that could get into really wild stuff. Because the client could like do something inconsistent, do something and then not be able to see the effect, or create a world in which these two things were completely inconsistent. And that would be fine if there was no one to perceive the inconsistency. But if there's someone who can see the fact that these two things don't agree, then you have your anomaly, right? You can also get into really crazy situations in which this is a form of network partition too, where like this machine can send messages to this machine, but the messages can't go back because there's a misconfiguration of the network card, or there was a misconfiguration of a level 2 switch, or something like this. Right? So you could, one-way mirror effects are an example of a network partition. Three-way partitions are an example of a network partition. Two-way partitions, and then just other weird ones where, one machine goes into a lengthy garbage collection pause, and for all intents and purposes, it's down. So it can't see these machines, but then when it wakes up from its garbage collection pause, it times out and it thinks everybody else is down. So in some sense, that's creating a partition of one, right? I think everybody else is down, and everybody else thinks I'm down, and in fact, everyone's up. Okay? Now, why am I saying all this in the context of models versus reality? Well, because omissions give us a really convenient way to model network partition, right? We just drop all the messages. Typically what I'll do is, I'll go like this. I'll be like, okay, that's the partition. And then I just simply don't allow any messages to cross it. We can talk about how our protocols proceed when there's this uncrossable line in the model. So any network partition of any length, just like we saw with crash failures, we can just model by dropping the appropriate subset of messages. Okay? I convinced you that the omission model contains the shit that can go wrong in TCP and the shit that can go wrong in networks due to network partitions. Despite the fact that individual RPCs getting dropped is not the way that these failures actually work in real life. Is everybody comfortable talking about omissions despite the mismatch with reality now that I've connected the two? Any questions? Concerns? Yeah. Things you're excited about? All right. Models versus reality. Session oriented protocols. Network partitions. Oh man, I'm flying today.
Wait, so this is back what you were talking about at the beginning when you were talking about what is software-defined networks, right?
Well, so software-defined networks are a newish way of doing data center local networking. The idea behind software-defined networks is instead of having pieces of software that we configure via configs and stitch together in various ways, what we should have is relatively dumb programmable devices, and then sort of a controller in the clouds that has the purview of the whole network and is programmable using some high-level, often declarative language. And in the controller, you write down your policies. Like there should be the following routes between these racks, and there should be a local firewall that blocks off this rack, and we should have a NAT over here, and all the networking stuff you could ever think of. Instead of sort of doing it on all the devices, you do it on the controller, and the controller in some kind of smart, synchronized way pushes that information out to the switches. Now this is nice for a lot of reasons for the admins, but it's also nice for researchers, because now we can start asking whether the distributed systems that we are writing, thinking mostly about them running on hosts, we can start to ask, how can we decompose them? Or like, what parts of those algorithms could run on the switches? Much faster potentially. So when we study Paxos, and I talk about Paxos, I'm promising Paxos, it's coming. Maybe we'll take a little bit of time and talk about some recent work. There's a really nice piece of work that came out of the University of Washington, Microsoft Research, called No Paxos. And the idea is one of the things that Paxos does is it sequences requests. Sequencing requests can be a big bottleneck, as we showed. Because in one node, and all the things go into asking for their IDs, we can only go as fast as this one node, right? And they're like, well, but routers and switches can dole out sequence numbers like super fast. So maybe there's a way to take the Paxos protocol and divide it into two pieces, base Paxos and the sequencer. And we put base Paxos on all these nodes, but then we put the sequencer on the switches. And so you kind of get sequencing for free. There's all this cool stuff that software-defined networks allow us to do now, hoisting distributed algorithms and protocols into the actual, the fiber, the wires. Yeah, so that's cool. But I've lost my train of thought. Right, so the main topic of today's lecture, broadcast, multicast, atomicity, reliable broadcast. So I haven't used the term yet, I don't think yet, but most of the communication we've looked at in this class so far, actually that's not even true. A lot of the communication we've looked at in this class so far is unicast communication. What do you think unicast communication means? Yeah, it's just one pass. Yeah, messaging between two endpoints, right? Sending a message from one computer to another. Unicast communication. And we talked a little bit, especially in the context of causality stuff, about broadcast communication. And what did we say broadcast was? You're sending a message to who?
To everyone.
To everyone. So this, in fact, I should try it. Sorry, note takers. One-to-one communication, right? One-to-all communication, right? Broadcast uses everything. And then we also saw at least one example in this class of multicast communication, which is going to be one method, but not necessarily all. Right? Yeah?
So every broadcast is technically also a multi-broadcast.
Sure. Except we lose information if we say so we say broadcast, but absolutely that's right. Does anybody remember which picture I like to draw as an example of multicast?
Total order.
That's right, the total order anomaly, because we have two clients that send not to everyone, but specifically to what in multicast would be called group, right? These two replicas are a part of a group in a really meaningful way, because in some sense they're trying to be the same computer. And so they're two computers, but they're role playing as this one very resilient computer. And what C1 and C2 are doing is multicasting to all members of a particular group, to all servers providing a particular functionality, but not to all servers, because if they did, they may be sending to each other as well. Right? Okay, so, question? Okay. I didn't say anything. Now, we've always assumed that Unicast is just built in, right? I didn't teach you anything in this class about how you send a message to another server. That's something you learn about in the networking class in CE, right? So we're just assuming that there's a primitive that allows you to unicast a message. But assuming that primitive, how do you think you would implement broadcast and multicast? Like, they're not given as primitives, yeah.
Using asynchronous or asymmetric encryption and handshakes.
Asymmetric encryption. What makes you say that?
Like the router could handshake with the client, and then they pass a certificate, and then now.
But I'm trying to understand, because we don't have any. We're not trying to provide a guarantee around authenticity of the message or unforgeability of the message. So what's a certificate for?
So that way, I guess it would be broadcasting to everyone, but only people with the certificate can decrypt it and understand it.
Yeah, I mean, I think you're jumping ahead, because we never stated a requirement around encrypted communication. So, but I think you could use a directory service. Like, you could say, like, if I don't know who everyone is, there could be somebody who was like the directory, and I could either ask him who everyone was, and then he or she replies to me, and then I could send my thing to everyone. Or I could do sort of the DNS recursive equivalent, where I could just say, I could ask the directory on my behalf to go ahead and multicast to everybody. Now, that second choice probably wouldn't be great, because the directory would be a bottleneck. But that's sort of almost a separate concern of how do we know who everyone is, or how do we know who many is? And that's what's called I'm going to break this down somewhere else. That's a problem of service discovery. Or, more broadly, the problem of membership in a distributed system, which is a really important subject, and we're going to talk about it a little later. How do I know that the whole world involves Alice, Bob, Carol, and Dan? Yeah.
At least in terms of broadcast, every machine that's up and online could be at least listening to one particular broadcast channel. And when you need to send a broadcast message, you just send it to that channel, and you don't care who else is on the other end, because anyone that's up is at least listening on that channel.
So let me ask you something. So there is such a thing as what you're describing. It's not used very much in practice, called IP multicast, where there's like a high address, UDP, that you can just bind to as if you were listening. But every person who binds to it will get all the messages addressed to it. When I was a lad, I used IP multicast quite a bit at ask.com. But do you think that would work on the wide area network?
No.
Okay. Would it make sense for my phone to be like listening for something? Yeah, so like that won't work at all on the wide area network. So let's try to come up with a solution to implement Unicast that isn't specialized, that doesn't use cute hardware, that makes a minimal set of assumptions. What can we do? Something that could work on the WAN at large scale. What can we do? Well, we only have one primitive, right? So presumably we're going to use this to implement this. Yeah, well, I mean, that's all there is to it, right? We'll implement Unicast, or broadcast, because we want to implement it in the most general possible way, by just issuing a series of Unicasts. Right? Let's not worry about the problem of knowing who all is out there. Let's imagine that we've somehow orthogonalized or postponed the problem of service discovery. We come into being knowing who everybody is. We'll address that later, how you actually know that. So if I want to send a message to Bob and Carol that says Bob smells, probably the easiest way to do it is to send a message to Bob that says Bob smells, and almost at the same time, or as close to at the same time as possible, send a message to Carol that says Bob smells. Okay? I made this point earlier in this class, and I want to emphasize it again, that pictorially, I'm always going to make the distinction between two unicasts and a multicast by drawing them either as separate lines as I would like, if I drew point I'm trying to make today, that stop me if this is confusing, is that when I draw this picture, nevertheless, under the covers, it's going to be implemented as Unicast. Because Unicast is the only way to send a message from one computer to another. And this introduces a problem because we want it to be one event. We want it to be one event in the sense of it being atomic and indivisible, right? We want the broadcast to either have happened or not have happened. And if the broadcast is indeed, under the covers, a compound event, there's a hazard that it could partially fail, right? That it could partially happen, which would be bad, right? Okay. This brings us to, oh, then multicast. What's multicast? Same thing. How do you implement it? Unicast. Multicast is a little trickier because there might be a great many subgroups of everyone. So you might have to have a lot more metadata to know how to do multicast. Because in some sense, you could multicast to the power set of everyone. Right? So if there's 100 things in the network, there's 2 to the 100 groups that you could multicast to. Yeah?
So in the case of something like a vector clock, would that be considered 2 sends, or would that just be 1 send?
Oh, that's a great question. That is 1 send. So we've actually attached that to the payload. And so this kind of atomicity hazard does not arise. And we know we can do that because Unicast gives us the ability to send some uninterpreted message M. And so we can always, we have some message, Q, and we can always say, well, I'm gonna put Q append my vector clock, and that's my M. And we don't put anything we want in M. And by doing so, we never have to worry about wild shit happening, like the message gets there, the vector clock gets there before the message that it describes, or the message gets there and its vector clock is lost, or the reverse. Right? You get atomicity in this case by packing all the information in the same packet. Yeah, Liz.
Well, if I could rephrase the question, I think what the question was is not does the message and its vector clock come together, but when you do that multicast, does every one of those messages have the same, are they considered different events with different...
Was that the question? Oh, okay, because I thought we answered that question before in the class. So if I draw it in this way, they are intended to be a single event, and they're guaranteed to have the same payloads. And if I do it in this way, not necessarily. So. Thank you, thanks for the clarification. Yeah.
To follow on with that, it seems like you're sending multiple unicasts, but you're counting them all in the same vector clock computation.
That's right.
Okay.
That's right. Now, reliable broadcast. What's that?
Did we use broadcast in one of the reliable delivery solutions prior?
I don't think so. I mean, all the reliable delivery, when you pose a reliable delivery problem, there's just two processes, right? So broadcast is kind of
We
trivialized.
did broadcast for
Causal
causal.
delivery, yeah. But we never said it had to be reliable. It's like kind of a whole separate problem.